Hello, this evening I decided I'm going to talk about the physics of gases. I've written up a whiteboard here and I'm going to sort of progressively work through it throughout this video. And this is going to be the first of two videos on the physics of gases. So Boltzmann is a real visionary here. In around 1900, he figured out that a lot of the experiments people have been doing in the 1800s was a big heyday for physics because they were finding like steam engines and things, and people were sort of throwing magnets together, heating up liquids and gases, and coming up with all these sort of crazy laws that were weirdly effective. But they sort of made sense. Magnetism, people found had like a relationship with heat, so there's sort of a proportionality thing people were using, and gases sort of had a compression ability, and their volume was related to sort of how compressed they were, which Boyle figured out. And yeah, people are just coming up with hundreds and hundreds of these laws about everything they could see around them. And right around, and so yeah, that created sort of the heyday of 1800s physics. Right around 1900, when stuff was sort of crowning, that's when Boltzmann was around, and he saw through it all. He saw that all of those descriptions could be united under an atomic description, and that each of those laws could be predicted as an effect of Newton's laws on the large scale when applied to systems made of atoms. And I'd like to demonstrate a little bit of that thesis in this video. And good first system is ideal gases. So to the left, you can see I've written a diagram of the system we're going to be working with. So the circles meant to be atoms, and sort of the arrows are them buzzing around. And the density of the gas is presumed to be low enough we can approximate the atoms as not interacting. And labeling the system as R. And there's a second system that's soon to be like sort of really insignificant, but it can exchange energy with the ideal gas. We're gonna need it for sort of the mathematics. But it can't change its temperature, and that's sort of out of it being like very insignificant. The energy that it can exchange isn't enough to really significantly warm it at all. And yeah, so that's the diagram of the system set up there. Yeah, it's a bit of a pipsqueak system. So in terms of the way we're going to analyze it, people found like classical mechanics, 1800s physics, looking at sort of all stuff they could see around them. People saw like they discovered the concept of momentum and energy, and saw that sort of they varied continuously. Things that could collide together any speed they thought, sort of they desired, and ultimately that was thrown up in upheaval when another revolution of 1900s is the quantum revolution, where people found that a lot of that stuff was actually discrete at sort of a micro scale. So the important thing to consider with this system is it can be the state of a system is defined to be sort of its ultimate description, just sort of description of its properties in an instant in time. And a quantifying detail of that system, or way to quantify that, is the number of states at a particular energy level. And so we can formally work from there. Sort of the energy, the number of states at the total energy is just the sum over the energy levels of the products of the number of states of the two S and R systems at the specified energy levels in the parentheses. And the system S is assumed to take on discrete energy levels, and the system R is assumed to be large enough to where it's sort of more continuous. But yeah, the number of states, it's assumed all energy levels equally likely. So the number of states at the energy total is just the sum over all the energy levels of the product of the number of states between the two subsystems. In in per energy level, the number of states of the system, if R just had one state, then the number of states at a particular energy level would just be equal to the number of states of S at energy level En. But if we assume the states of R are sort of numerous, then there's a possibility that R could have multiple states at a particular energy level. And so you got to multiply that to get the full number of states of the system at a particular energy level, because R might not necessarily, the ideal gas might not necessarily be sort of that trivial and have multiple states at a particular energy, multiple possible states at a particular energy level. So the total number of states is that number of copies of the number of states of the smaller thing at the En. So, but we could change the summation, make this simpler, and sum over N instead of the energy levels. And summing over N reduces the sum to just the R term, because in that regard, yeah, we're taking into account S's multiplicity. And we can then reduce the sum, or air quotes, simplify it by bringing up the number of states into the actual exponent. Using log and the E natural exponent, and adding in a copy of Boltzmann's constant, multiplying the exponent by 1, we actually can relabel the top as the entropy, which is just the log of the number of states at a particular energy level. And working in terms of entropy is makes things a lot simpler. And it's just a mathematical convention that is notationally convenient. So we're assuming that the total energy, the energy of the ideal gas, super way dominates S, which means that it's greater than any energy level S could be at. So number of states total, we can Taylor expand the entropy. And this goes to the first term. And this is sort of like taking the tangent line of a curve and approximating the curve using that tangent line. So there's one equation that won't be able to prove in this video, which is the definition of temperature as a derivative of slope of the entropy function. And subbing all of that in, the Taylor expansion and temperature, gives us this really solid approximation for the number of states at a total energy level as a term times sort of a sum over N. And the chance of a system being in a particular energy level is number of states at that level divided by the total number of states. And number of states in level N is just one term of the sum, because each term is the contribution at that energy level. And that's till next video.